Welcome to this video. In this video we're going to talk about penicillin antibiotics. This video is going to be in the playlist on antibiotics and antibiotic resistance, so if you're struggling to find the different parts to this video, look in that playlist. Right, so the first thing that I want to say is that penicillin is not a single antibiotic. That's a common belief that is incorrect. That penicillin is just one antibiotic. It's not. There are absolutely loads of different penicillin antibiotics. Penicillin is an entire class of antibiotics that all have very similar structures and which all work to kill bacteria in the same way. Okay, so the first thing that I want to begin with then is looking at the core structure that all penicillin antibiotics have within their chemical structure. And then what I want to discuss is the mechanism by which all penicillin antibiotics actually work to kill bacteria. Okay, so we will begin then with the core structure of a penicillin molecule. What do all the different penicillin antibiotics, and we will go through the notable different examples of penicillin antibiotics later on, what do they all share? Okay, we're going to draw the core structure of penicillin. So, I'm going to draw the core structure of penicillin as its skeletal structure. And remember, in skeletal structures we don't show carbon atoms, they're implicitly shown by corners in a skeletal structure. We also do not show hydrogen atoms coming off carbon atoms. Wherever you've got missing bonds coming off carbon atoms, it's implicitly understood that those will be two hydrogen atoms. Okay, so I'm going to draw a skeletal structure for the core penicillin structure. Right, so the bit that I'm going to begin with is the beta-lactam ring, which is a very famous part of the core penicillin structure. So a beta-lactam ring is an unusual structure in chemistry because it's a four-membered ring. Now, three of the members of the ring are going to be carbon atoms, and one of the members is going to be a nitrogen atom. So here's our nitrogen atom, and then we've got three carbon atoms here. And this carbon atom down here is going to be double bound to an oxygen atom, and is therefore going to be a carbonyl group here. So this portion of the penicillin structure, and this is not the full core penicillin structure yet, this specific portion is called the beta-lactam ring. So this four-membered ring where one of the members is a nitrogen atom and one of the carbons in this beta-lactam ring has a double bond to an oxygen and is a carbonyl group. Okay, now, penicillin, the core structure of penicillin has another ring attached to the beta-lactam ring, known as the thiazolidine ring. So the thiazolidine ring is a five-membered ring, a more normal number of elements to have in a ring. And it's going to be a ring that contains three carbon atoms and a nitrogen and a sulfur atom. Okay, so the sulfur atom is now going to be up at the top here, and then the carbon atoms are going to be like so. So we have this five-membered ring attached to the beta-lactam ring. So this ring is what's known as the thiazolidine ring. Okay, now the thiazolidine ring, as I say, it's a five-membered ring where all of the bonds are single bonds, as we've got here. Three of the atoms in this ring are carbon atoms, and then one nitrogen and one sulfur, and importantly, the sulfur has to have two carbons, one on either side of it. It's bound to carbons both times, so you don't have the nitrogen up here, for instance. Okay, so this is a thiazolidine ring, and I'll just colour in the thiazolidine ring. So this portion here, which I'm now circling in orange, this is the thiazolidine ring of the penicillin core structure. And this portion that I'm circling in red, this is the beta-lactam ring of the penicillin core structure. Now, off the thiazolidine ring, all penicillin antibiotics have certain side chains. Okay, so we're going to have two methyl groups coming off this carbon. So this carbon has one bond to a sulfur, one bond to a carbon. It's still got two more free bonds, and we've got two methyl groups coming off there, and they're just shown in this way in the skeletal structure. And this carbon down here is going to have a carboxylic acid group coming off it. So I'll show this like so. So here's the carbonyl group, and here is the alcohol group. So that's a carboxylic acid group. So all penicillin antibiotics have this within them, and we're not quite finished yet. Okay, so all of this is looking fine, and this carbon will have another hydrogen coming off it, filling in its final bond. The nitrogen's got all of its bonds, the sulfur's got all of its bonds. This carbon will have a hydrogen coming off it to fix the final bond number up to 4. What about this carbon over here? Does it just have 2 hydrogens coming off? Well, no, there's something else coming off over here. It's going to have a nitrogen atom coming off it, like so, with a hydrogen, and then this is going to have a carbon coming off it here in an amide link. So this will have a carbonyl group, like so, and then you'll have a side chain, which is the bit that isn't fixed here. This is the bit that can vary. Okay, so what have we done here then? We've got an amino group coming off this carbon here, which is attached via amide link to the carboxylic acid group of some side chain here. So we've got an amide link here off the side of the beta-lactam ring, and then the final bond of this carbon here will be to a hydrogen atom. So this R here, this is the portion that can actually vary. Different penicillin antibiotics will vary because they'll have different R groups here. And this portion that I've got in green here, this is known as the acyl side chain. So all penicillins have the same beta-lactam ring, the same thiazolidine ring, the same things coming off the side of the thiazolidine ring. What differs between them is that they all have different acyl side chains. The carboxylic acid that is bound via the amide link to all of this structure here differs between the different penicillin antibiotics. That's what varies. Okay, and this now is the complete core penicillin structure. Okay, sometimes called the core penicillin nucleus. Okay, so if you hear people refer to the core penicillin nucleus, it just means the core structure of the penicillin molecule, rather than this portion that isn't the core portion and varies between the different penicillin antibiotics. Now, it's this core penicillin nucleus that actually has its antibacterial effect. This portion just alters the properties of it, for instance, the pharmacokinetics of the drug. This is the portion that actually is going to inhibit a certain enzyme and lead to the death of the bacteria. Right, so there's the core penicillin structure. All the penicillin antibiotics look like this. What differs between the different examples of penicillin antibiotics, which we'll come on to later, is what you actually have in this R position here, what the acyl side chain of the penicillin actually is. Okay, right. So what I want to turn my attention to now is discussing the mechanism by which all penicillin antibiotics work. We've discussed the core structure of penicillin antibiotic. Let's now actually discuss the mechanism. Now, in order to discuss the mechanism of penicillin antibiotics, we need to know a little bit more about the structure of bacteria. Specifically, I want you to know about the fact that bacteria have cell walls. Okay, so I'm not going to make too many assumptions about your level of bacteriology, so I'm going to go back to the very basics and talk about the 2 major categories of bacteria. So most bacteria, but not all bacteria, fit into one of 2 categories, and the 2 categories are gram-positive bacteria, so I'll just put gram-positive, this is my shorthand for positive, and gram-negative bacteria. These are the 2 main categories of bacteria. Now, most, but not quite all bacteria fit into one of these 2 categories. And these 2 categories of bacteria have very different structures, but they both have cell walls that are made out of the same stuff. And penicillin antibiotics are going to work by causing the destruction of the cell wall of bacteria. Okay, but I do just want to talk about the different structures of these 2 categories of bacteria. So gram-positive bacterium. The structure of a gram-positive bacterium looks like this. You have a cell membrane, which I'll show here, and then surrounding the cell membrane you have a hugely thick cell wall. So I'll show this in orange here. So all of this coloured in orange, this is going to represent the very, very thick cell wall of a gram-positive bacterium. Okay, so all of that is the thick cell wall of the gram-positive bacterium. So I'll label up the different portions here. So this is the cell wall in orange, and then we've got the cell membrane within the cell wall there. Okay, so that's the basic structural understanding that I want you to have about gram-positive bacteria. And as I say, loads of different species of bacteria fall into this category of bacteria. So for instance, all the Staphylococcus species, Staphylococcus aureus, Staphylococcus epidermidis, and all of the Streptococcus species, so Streptococcus pneumoniae, for instance, all of those fit into the gram-positive category of bacteria. On the other hand, the other major category of bacteria are the gram-negative bacteria, and these have a slightly different structure. Okay, the structure of gram-negative bacteria is that you will have a cell membrane again, then you'll have a very thin cell wall this time, so a much thinner cell wall in gram-negative bacteria, and then outside of that cell wall you'll have another membrane called the outer membrane. So let me show this here. So now outside of the cell wall, the thin cell wall, you're going to have another membrane called the outer membrane. So let me label this up. So the inner membrane is the one that's actually called the cell membrane. Sometimes you'll see that just described as the inner membrane. Then the outer one is usually called the outer membrane. This is not considered the cell membrane, but of course it's the same structure. It's a phospholipid bilayer. And then of course we've got the thin cell wall in between the cell membrane and the outer membrane, and the space which contains the cell wall, the space in between the cell membrane, the inner membrane, and the outer membrane, the name for that is the periplasmic space. Peri means around, so it means sort of around the cytoplasm. Okay, the periplasmic space. Right, so that's the basic understanding of gram-negative bacterium that I want you to have. And examples of gram-negative bacteria are Escherichia coli, E. coli, Pseudomonas aeruginosa is another example of a gram-negative bacterium. Okay, or bacterial species. Right, so most bacterial species fit into this description, i.e. they have this sort of structure, or they have this sort of structure, and they are described as gram-negative. Right, the point is here that they have this cell wall, and penicillin antibiotics are going to work by causing the destruction of the cell wall. So how is it that penicillin antibiotics lead to the destruction of the cell wall in these bacterial species? Well, to understand that, we're going to have to understand the structure of the bacterial cell wall in more detail. So the cell wall is made up of what's known as peptidoglycan. Now, peptidoglycan, the name tells you a lot about this. Glycan tells you that this is carbohydrate-based. Peptido tells you that it's peptide-based. Now, the one that is towards the back, the suffix or the last portion, is the more important one. So this tells us that these are very long carbohydrate molecules with little bits of peptide as the side chains. Okay, if it was the other way around, glycopeptide, then that would mean that the main structure was a peptide, and then just as little side chains you have carbohydrates on the side. Peptidoglycan is the other way around. It means carbohydrate is the main structure with peptide on the side. So these cell walls are made up of these peptidoglycan molecules, and these are enormous great fibres. So peptidoglycan are huge great fibres. So around the bacterium you're going to have loads and loads of these peptidoglycan fibres, which are huge great fibres making up the cell wall. Again, as I say, most of the fibre, the main sort of length of the fibre, the main polymer is carbohydrate in nature. It's monosaccharide after monosaccharide after monosaccharide after monosaccharide, all joined together in a great big polysaccharide. But off the side you're going to have molecules that are peptide in nature. Okay, so off the side you'll have little side chains, which I'm colouring in pink here, which will be sort of peptide side chains like so. Okay, attached to the main carbohydrate molecule. So if I draw some more of these, the cell wall is going to have loads and loads of these peptidoglycan fibres all running in parallel around the bacterium like so. So here are some more of these peptidoglycan fibres, and I'm just going to add on their peptide side chains as well. So here are some more peptide side chains like so. And the way that we can actually join these together then, the way that the peptidoglycan fibres here can actually be joined together to actually form a strong cell wall structure is that you can join these peptide side chains together. So what you can do, what we will see an enzyme does in a moment, is it joins the peptide side chains of the peptidoglycan fibres together to tangle all of these peptidoglycan fibres together and build a strong structure. So overall, the cell wall in both gram-positive and gram-negative bacteria, where it's made out of peptidoglycan, which is a huge number of bacteria have peptidoglycan cell walls. It consists of loads and loads of peptidoglycan fibres, which are mainly carbohydrate, but as little side chains have peptide molecules. And the way that it's all held together is that the peptidoglycan peptide side chains can bind to one another to overall form a shell that will be strong and which will surround the cell membrane. Okay, so what I want to now tell you is the name of the enzyme that forms these cross-links between the peptidoglycan molecules. This is called peptidoglycan transpeptidase, and it is this enzyme that is going to be blocked by penicillin. Penicillin antibiotics are going to work by blocking this enzyme, and I've put the wrong thing. Transpeptidase. Peptidoglycan transpeptidase. Okay, so all of the penicillin antibiotics, which have this core penicillin nucleus that we've now seen, work by inhibiting the peptidoglycan transpeptidase enzyme. Now, what's that going to lead to? Well, that's going to mean that we can no longer cross-link our peptidoglycan chains. Okay, so that means that we're not going to be able to build a good, solid cell wall, because of course if you just have loads of peptidoglycan fibres lying in parallel, that's not very strong at all. You need to have them all connected together via these cross-links in order for it to actually form some solid structure which is capable of protecting the bacterium. Okay, so we're starting to see why this might have cause a problem for the bacterium. However, you might ask now, but what if the bacterium's already got its cell wall built? Okay, it's a very logical question to ask. If the bacterium's already got its cell wall built, it's here, it's got a beautiful cell wall, it's already got all of the cross-links between the peptidoglycan molecules there, it doesn't need this enzyme, surely. So blocking this enzyme is going to have no effect on the bacterium. Why will penicillin antibiotics kill this bacterium when it's not actually using that enzyme? Well, the answer is it always is using that enzyme, because the cell wall is not a static thing. The cell wall is continuously being remodeled. So, there are also loads of enzymes whose job it is to break these cross-links between the peptidoglycan molecules, and continuously a bacterium is using these enzymes to break the cross-links between peptidoglycan fibres, and then peptidoglycan transpeptidase rejoins them back up. And this is so that the bacterium can remain reasonably flexible, because it doesn't want a constant solid cell wall. It wants to be able to continuously remodel its cell wall. Okay, so it relies upon the continuous breaking of these cross-links between peptidoglycan fibres, and then the continuous rejoining together of them so that it can remodel its cell wall. So, here comes the answer as to why penicillin can actually lead to the destruction of a cell wall in this bacterium that already has its cell wall built. It's now, let's say this bacterium has now been exposed to penicillin. Penicillin will inhibit all of the peptidoglycan transpeptidase enzymes, all of the enzymes which do the opposite job of breaking the cross-links between the peptidoglycan fibres. They won't be inhibited. Okay, so now what will happen is all of the cross-links will get broken, and of course what's supposed to happen is it's supposed to be a beautiful balance, a beautiful dynamic equilibrium between breaking the cross-links and reforming them, but now we've got rid of the reforming bit, so now the enzymes that break them are just going to break them, but nothing's going to reform them. So gradually all the cross-links are going to get broken. What the cell will now have around it is just loads and loads of peptidoglycan fibres that aren't interlinked into a solid meshwork that forms a nice hard cell wall to protect it, and this will just sort of disintegrate away, so the cell wall will break down around the bacterium. Now, why does the bacterium losing its cell wall mean the death of the bacterium? Well, the answer is that the cytoplasm of a bacterium, so the portion inside the cell membrane, is extremely hyperosmolar compared to the extracellular fluid. Okay, there is a very high concentration of solute inside there, so I'll draw, well, get a colour actually. There's loads of things inside a cell. It's very, very concentrated area. Okay, you've got loads and loads of things dissolved in the fluid there. So it is hyperosmolar, there's far too much solute in there. So there's much more solute inside the cell membrane than is outside of the cell. And that means that there is an osmotic gradient favouring the movement of water into the cytoplasm of the cell. Now the reason water doesn't usually go down this osmotic gradient is because it simply can't. There isn't room. The cell membrane has a finite volume. Okay, so you can't just bring loads of water in here, even though it would be going down its osmotic gradient, because this simply can't get any bigger. Okay, and what's blocking it getting any bigger? Well, it's the hard cell wall that surrounds the cell membrane. The cell membrane, you know, that's just a bag of gloop. Okay, that doesn't have any structural toughness to it at all. The cell wall is what's tough, and that's what is blocking the expansion of the cell membrane and blocking, therefore, the water entering the cell cytoplasm. Once the cell wall has gone in both of these cases, although I'm just pointing to this one, now what will happen is water will move into the cytoplasm of the cell down its osmotic gradient. Okay, the cell will now just engorge. It will get bigger and bigger and bigger and bigger and bigger until the cell membrane just can't cope anymore, and it will burst, and then the cell will just be obliterated. It will go everywhere, and that process, the fancy name for that process, is the bacterial cell will undergo osmotic lysis. Okay, breaking apart because of osmosis. Okay, so this is how penicillin antibiotics lead to the death then of bacteria with peptidoglycan cell walls. Okay, so they are described as bactericidal antibiotics because they are actually capable of killing the bacterium rather than just stopping it dividing. So there are two major categories of antibiotics: bactericidal ones and bacteriostatic ones. Bacteriostatic ones don't kill bacteria, they just stop them dividing. Bactericidal antibiotics are ones that actually do kill bacteria. Penicillin antibiotics are examples of bactericidal antibiotics. They kill the bacteria. Okay, but of course you do need your bacterium to have a peptidoglycan cell wall. If you've got a bacterium, a bacterial species that doesn't have a peptidoglycan cell wall, then the penicillin antibiotics are going to be totally useless. And most bacterial species, well, a lot of bacterial species that are relevant for human medicine do have a peptidoglycan cell wall, and therefore penicillin antibiotics are bactericidal against them. Okay, so we'll have a break here. In the next video, what we'll do is actually begin discussing the different examples of penicillin antibiotics.